Hello, welcome to week 2 of our adventure. So in section 4.4, we are using the tools and techniques we did in section 4.3, the section about how differential equations are equations too, and we're going to apply it to the problem of world population growth. And then for your homework, you're going to do a different problem. It's easier. I'm doing the complicated one for you right now, okay? So world population, that's a thing that's been worrying people since the 18th century, the fact that there's going to be too many people. So there you see a graph. The data comes from the UN. And so in blue, you see world population. And so the dark blue is up to 2015, when the world population was 7.4 billion. And the light blue is kind of like the projected world population later on. So it looks like we might get around 12 billion people in the world sometime in the next century. How do they get that? How do they do the projection? So that's what we're looking at. They use models, and we're going to have a look at models. So the line in red is the annual growth rate. And you see that for quite a while, the world annual growth rate was pretty constant. It looked around 0.6%. And then in the 1920s, you can think about reasons why that would be, better sanitation and health and food supplies and all this. So basically what happened was people stopped dying as much, but they still were basically having as many babies as before. So the growth rate shot up to like 2%, and that was kind of like the peak around the early 60s. And since then, we've seen a decline in that growth rate. So now it's just a little bit over 1%. And they're thinking that, maybe by the end of the century, it's going to drop down to like 0.1%. Who knows? Anyway, so let's model population a bit. So we're going to look at 2 models of growth. We looked at these back in section 4.1.1. There's the constant per capita growth model. And in that section, we looked at the situation in the world around the year 1990, when growth rate was around 2% per annum, and there was 5 billion people in the world. So our model is P prime equals 0.02p, the 0.02 being the 2% growth, and P0 equals 5 standing for 5 billion. And we're going to compare that with the supergrowth model, which is the one where the growth rate is increasing over time. And the one we looked at was Q prime equals 0.015 Q to the 1.2, the power 1.2. And again, Q0 equals 5 because we've got 5 billion. And I don't know how carefully we looked at that, but if you did, you would have basically seen that between 1980 and 2040, so that was a period around 60 years, both models gave pretty much the same answer. But when we looked into the future, 2230, so like 240 years after 1990, we can't get the super growth model to stabilize. Something's wrong with it. And so we're now going to have a look at the solutions to these equations, and that'll explain more what was happening. So the easy one is constant per capita growth, because we know which function has as its derivative a constant multiple of itself. That's the exponential function. So just for ease of notation, we're going to center our times at 1990, so that t equals 0 refers to 1990. So that means p is equal to some constant times b to the t, where b is the base. And since at t equals 0, we have 5 as the p, our model is p of t equals 5 times b to the t. So we've got to find that base. Now we know that when we take a derivative of an exponential function, we get the exponential function back times a constant depending upon the base. So some of you know how to figure out that constant already, but for those not in the know, what we have to do is we have to find a base such that constant is 0.02, i.e. that means the derivative of b to the t at 0, we want to be 0.02. And so what I do when I want to compute is I make up an Excel file. So the next slide shows you this Excel file pop that I made. There's a copy on Blackboard that you can look at to see what I did. So basically you see it's just the microscope file that the microscope file that I've used before, except I've done it so that I can change the base, and I'm based at 0. The base point is 0. The base is whatever that number b is, and sort of down in the lower right corner you can see what the slope is. And so basically you play around the b, you know, as b increases, the slope increases. Okay, so it's not too hard to find. You know, it took me I don't know, 5 minutes to get it to 8 decimal places, so that's pretty good. So I found a base of 1.02020134 gives us a slope of 0.02 at the origin. So that is our base. So that is our solution. It's 5 times that base to the t. So this constant per capita growth, it's also known as exponential growth. Okay, and we know that's a solution because we've verified it. Okay, we've plugged in 0 and get back 5. We take a derivative and we get the function back timed 0.02. So that is a solution. What can we do with that? Well, a useful trick is it's possible to change the base if you change the exponent. And so we can write it as the base is 2 if we divide the exponent by 0.693. Okay, and the reason why that works is because of the chain rule, right? You let u equals kt divided by 0.693, so that when you take the derivative of that, you get k divided by 0.693, and when you've got a base whose the base is 2, you take the derivative, you multiply it by 0.693, and the 0.693s cancel out. Okay, and the reason why that's good is because now when kt divided by 0.693 is 1, that means the population is doubled. And so that gives us a formula for the doubling time. So doubling time is kind of like the growth version of half-life. So you might have heard of half-life in decay problems, where you get doubling time in growth problems, like the time it takes for anything to double. And so if we look at 0.693 divided by 0.02, that gives us 34.66. So that means by this model, the world's population is going to double every 34.66 years. Okay, interesting information. Supergrowth. Okay, here the solution is there. It's quite complicated, but it's easy to verify because we've got a nice chain. Okay, so we get u equals 5 to the power negative 0.2. That's just a constant, so don't worry about it. Minus 0.003t. And we let q equal u to the minus 5. So, using the chain rule, we just take the derivatives. So the derivative of the u is just minus 0.003. Remember that 5 to the power, it's just a constant, so it disappears when we take the derivative, and we just get the negative 0.003. And we take the derivative of q, we get minus 5 u to the minus 6. Okay, and so what we do then is we just multiply those things together, and the negative 0.003 times negative 5 is 0.015. And that's exactly the constant that was in the model. And we get whatever that u is, that 5 to the minus 0.2 minus 0.003t, that u, we get that to the power minus 6. Well, minus 6 is 1.2 times minus 5. So we've got that q prime equals 0.015 q to the 1.2. So that equation works. Got to check the initial condition. So q of 0, t becomes 0, so we get 5 to the power minus 0.2 to the power minus 5s, right? So the minus cancels, 0.2 times 5 is 1, so you get 5. So that's why you get that funny number there. So we have it as a solution. Okay, now we can see what a problem. Because q is something to a negative power, so that means we're dividing by something. So when that something we're dividing by becomes 0, we get problems. And so that asymptote is going to be when that number equals 0, and that happens at t equals 241.6. So we have a vertical asymptote when t equals 241.6, and that's why we had that trouble finding q of 240, because in fact, if you plug that number in, because it's very close to 0, and we reciprocate it, and we take it to the 5th power, that's actually 400 quintillion. So you get millions, billions, trillions, quadrillions, quintillions. So it's a really, really big number. It's a ridiculous number. So here I've got q and p, and I've made a semi-log plot. A semi-log plot means that the horizontal axis is normal, but the vertical plot, you see it goes 10 to the 1, 10 to the 3. When you go up by unit, it's a log plot, right? Because it's going up by powers of 10. And semi-log plots are really good because if you've got something that's exponential and you graph it, you get a straight line. So you see P there is a straight line. And you see that Q, again, as we predicted for the first 60 years, it sticks pretty well to P, but then it just shoots off to infinity. Okay, and so we see our problem. That's why it doesn't work. Okay.